Good morning. This is Miss Jody coming to you with our first video for Earth and Space Science, the Tuesday class that meets 9:30 to noon. This has been an interesting process. I'm very sad to be away from you, but we do want to continue on with our work because we may be home a little longer than what we want, and so just in case, then we can keep up with a few things. So what I'm doing is we're going to continue with the journals because we're at the end of the year and we want to keep these going, and we're hoping to be able to get back together. And when we do get back together, hopefully, then maybe we can spend our time working on some experiments and the crafts that will fill the journal. So for instance, like the artwork that you were working on that went along with our study of the solar system and turning our eyes upward after we spent almost the entire year studying Earth and all of its systems. We turn our eyes to space, but this particular artwork, which isn't finished, this must have been the one that Miss Eden or Miss Olivia started for my book. Those sorts of things I still want to be able to do, but we can't do it together because we're at home. So what I thought is, what about us working on our notes, because this is some of the stuff that you can get done, and then when we come back together, I'll leave spots in the journal for us to add all of our crafts and the experiments and pictures from our experiments when we get to do some of those fun things. So the more we get done with our notes and our lessons, then the more activities we'll get to do when we get back together and just spend our time that way. So that should be fun. All right, so with the notes, it's going to be a little difficult because obviously you don't have your journal. So what I've been doing with my classes, explaining to them to go ahead and take your notes on a half sheet of paper. So I just took one piece of paper, folded in half, and cut it like a computer paper or whatever. And the half sheet is going to be perfect because as you're taking your notes, then when we come back together, as you can see, we'll still have the label in the journals, and see how the half sheet will just glue right there over top of the space where the notes would have been taken in the journal. So this will be a way where we can still do our note taking, and it will help us with being able to still have our own personal hand notes in the journals. Now, to keep track of it, what I would do is, if this is the notes for our solar system, then I would just write that on the back, our solar system, and then put all the notes in it. Because you don't want to write our solar system at the top because you're going to have a label there anyway. So I would just write it on the back, and the back is going to be glued in anyway, so nobody would see that, and that way we can keep track of what note page goes to what page in the journal. Okay, so, and obviously when we use my notes, a lot of times I have a little more detail than what you necessarily have to write down. And so if you want to skinny it down a little bit, that's fine too. And especially the younger ones, of course, we like to give them a way of taking notes that's more visual with drawing pictures. And so for you little ones, if you decide to do some of these notes, you can just do the same thing, get a little half sheet and draw out some of the things that I have marked out, and you don't have to write all those big words. You know how we normally do when we take notes, little ones, we maybe we write one of the words to practice our writing, or the numbers or something, and then we draw the pictures. Okay, so you can still do that, so you don't have to get overwhelmed. And parents, if you're working with the younger ones and they don't want to do much of the notes, that's also fine. They can follow along with us and try to grasp it with what they can, and then I can photocopy my notes even and put them in their journals if they want some notes, or if not, I'm sure they're okay with however much they want to do. Right, but you older students, which would be the 4th through the 8th grade, yeah, 4th through the 8th grade, or 7th, you should be taking some good notes. All right, so this is just showing you sort of where we were in our studies. Now, turning our eyes to space after spending all that time talking about the Earth and all the amazing systems and the atmosphere and the hydrosphere and the land sphere and all of those things that we saw on our Earth. Now it's time, and it was time for us to take a look upward at everything else that's out there. And we realized by watching some of our videos how vast this space world really is. It is so hard for us to get our minds wrapped around it. And that's because usually we have things like these types of pictures, like these solar system ways of seeing how it works, you know, the sun, Mercury, Venus, Mars, you know, the asteroid belt, and then the 4 outer planets. And so we have these types of drawings, and when you see them, they're helpful for you to memorize the planets and what's all out there, but they're not very helpful in the fact that this is not a good scale of really how big things are, how far they are. And if you really wanted to show really how far they are, you wouldn't be able to put it on one poster. You'd have a poster that wrapped around the entire science center just to give us an idea the distance between the sun and Mercury, and then from the Mercury to Venus and on. And so these big sizes are hard for us to comprehend. So if you remember a couple weeks ago, we watched some videos that gave us a size comparison so we could understand even that our sun, as big as it is still tiny compared to many of the things that we've discovered in our universe using all of the great technology thus far. So we have a big place to study, and it's not going to be enough time to go over every detail, and especially in the book. If you're following along in the book, we're actually let me see what chapter this is, because we kind of spend a little bit of time on each chapter. Okay, so it's chapter 10. And it's called Consider the Heavens. And we already talked a lot about how man began to discover what was out there and how we were limited, right? So we're limited with starting from just being our feet on the ground, and this is all we could see and look up and try to figure it all out. Then we were able to escape velocity and able to put telescopes in space and man in space, and to be able to figure out a different perspective. So we were able to study even more. But as we go through chapter 10, you'll realize that there's so much in it, and there's no way that we can go over every detail. That's why I like you to have the book at home so that you're following along and you're reading and you're pulling out some extra stuff that we don't have time to go over. Okay, so as we go along, I'm going to have to skinny it down a little bit, and especially when we get to a topic like our solar system, because we only have 2 pages of notes for it, so we're going to just have to jimmy it down. But one thing I am going to do, like the videos that we watched before about how vast space is and what's all out there and the sizes, I have a video that will be posted to your Google Classroom that I set up for you, and it will give a visual of how we can create a scale model here on Earth. And it's still very big because we need a big giant desert to kind of do that, but that will give you an idea of just our solar system. So when we study our solar system, even that is going to be really big but really small compared to everything else that's out there. Okay, and again, this type of poster that's supposed to be very helpful for memorization is not helpful for really understanding those vast sizes in that vast world. So that video will really help you. And that video is different than the one we watched before. The ones we watched before were just showing us a whole bunch of different things out in space, not just our particular solar system. And when you start talking about our particular solar system, I couldn't find a real good picture of the Milky Way. Obviously, we don't have a real picture of it, but because we're inside it and we haven't been able to our space technology hasn't been able to get barely out of our solar system. And we know Voyager was able to, we talked about that, get the farthest, Voyager 1. And I will be attaching a video on the update of Voyager 1 and Voyager 2 as of 2018, 2019, where they were and how far they had gotten. And just to give you an idea of the space probes that have gone the farthest. And even that is barely out of our little tiny solar system. So to get a picture of the entire galaxy, like if we wanted to take a picture of the whole galaxy, if we can't even get out of our little solar system, we definitely have not gotten out of our entire galaxy to take a little selfie or a snapshot. So I didn't find a real good picture of a galaxy of the Milky Way galaxy, but I don't really necessarily need that. I just wanted to be able to show you just an idea of what I'm talking about when we're talking about our solar system, how small it really is in comparison to a big giant galaxy. So here's a big giant galaxy. It's not our galaxy, but it's a spiral galaxy. Okay, so say this was our galaxy. We would just be like, our little whole entire solar system would be one of these little tiny stars, not even this brightest star, but let's just take that guy and let's say that would be ours. So if our little sun, and then our entire solar system, everything that's going around it, Mercury, Venus, Mars, asteroid belt, all those things, and then a little farther out after, our outer planets, and then the Kuiper belt and all that, all of that would just exist in this little tiny area. So it's weird to think, because we think of that, oh man, the Kuiper belt and then the Oort cloud and just all this big giant stuff, but yet we're really talking about, and the distance is being so far, but we're really talking about something small when it's in comparison to this big giant galaxy. Now that would just be one galaxy among millions of galaxies. And later on, when we get to a part in our studies, there's going to be a tab that says we're going to study, of course, the solar system. We're going to study asteroids, comets, meteoroids. We're going to study constellations, stars, suns, similar. And then what's the other one? And galaxies. So we're going to study all that. Then I made a tab that just says and beyond. And the reason I wanted to add that and beyond is because there's even more beyond that. And we talked about that when we talked about how the scientists were able to get a picture of the Hubble Deep Field, the picture that showed us that even in a small little tiny dark square of space, from our perspective, lay many galaxies that we didn't even know were there, that we were able to detect through Hubble. So we'll talk more about that when we get there. So that was just a picture of one galaxy, and we would just be one little star in that galaxy, in our little solar system, our little tiny sun, and it'd be rolling around, all of our planets going around our little tiny sun. So it's a big, vast world and so much to discover, and we're not going to be able to cover all of it. So you're going to have to dig in your book and spend some extra time. Okay. All right. So far we had already started this page for our solar system. Now we did a little bit on the sun and the star world, and that was just so we understand a little tiny side of the sun. We will do a whole bunch about the sun and stars when we do an entire tab that has to do with sun, stars, and galaxies. Okay. But we wanted to understand this big ball of fire that was giving us our source of life, which we call our sun. And so we talked about the processes that scientists believe are going on in the sun, and the what we call nuclear processes. And that's when you're messing with the nucleus of atoms. And so a lot of crazy, wild energy things going on here. So we talked about when we mess around with the nucleus of atoms, we do the process called fission, if you remember. Fission is what happens when we are creating energy to help us create electricity in our nuclear power plants here in in America and other countries. And so we have these nuclear power plants, and what we're doing is we're trying to take a big old giant atom. Well, we know atoms are so small, couldn't even see them, right? So when I say giant, I mean he's still really, 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 really small, but big for the atom world. So we got a big atom with lots and lots of things going on. Sometimes I refer to it as a fat atom, and I don't know why I do that, but he just seems like he's just got a whole bunch of stuff going on, a big old giant atom. And so what we do is we take particle and we shoot it at the atom, and then we split it. When it splits into smaller atoms, and there's some energy released. And this is not a good representation of the energy release, right? A little squiggly. We're talking about boom, and so much energy that when you split atoms, you better have it contained or you're going to blow up everything. And it's going to be very dangerous too, not just the blowing up. We then have different things flying off the atoms, and that's a very bad situation. That's when we have radiation, if you've ever heard of that. So we better be careful, and we obviously have good protocols for our nuclear power plants, but this is the thing we're doing. Now remember how I tried to tell you, and I'll do this one, I didn't do it in my notes, but I remember having you guys do it. For the word fission, if we got two S's, right, that helps us remember that they've been split apart, okay? So when you're splitting apart atoms, two S's. But then there's the other process that's similar to that, still messing around with the nucleus of the atom, and that's what we call fusion. So you see the one S there? Remember I had you circle that? The one S means I'm going to take the atoms and I'm going to squeeze them together. And I'm just squish them, right? Now with the squishing of the atoms together and forcing them together, this I gave an example of two hydrogen atoms and squeezing and pushing them together and creating helium, which is it has basically two of the protons in the middle, which would have originally been the two hydrogens, and it releases a whole bunch more energy too. And so if you look at the notes of a younger student here, I actually have Lily's. Remember this, Lily? So here's your beautiful sun. Good job. And then remember we had the fission with the two S's being separated, and then the fusion where we take the two atoms and we squeeze them apart and create the helium. Excellent. So this would be an example of how we could do the notes for the younger ones. And parents, I don't want you to get too stressed out with having to sit down and do all these notes with them and stuff with the younger ones. The older ones, they can just follow along. They're used to my style. They know what I'm expecting. The younger ones, you just do whatever you feel appropriate for the note times if you want to do the notes. And we could glue some stuff in here. You want to make extra pictures, whatever. That will be fine. Okay? But going back to the fission and fusion. So we do this in our nuclear power plants, the fission, and the fusion is what we think is going on in the sun. So we think that the particles are kind of actually not even maintaining as atoms. There's so much energy and so much knocking into each other sometimes, but then eventually we've got all of this fusing together that's creating more and more energy. And you've seen a picture of the sun before. Brilliant, beautiful. And I am attaching a video that is just basically a tour of the solar system, a kid's version of tour of the solar system that will start with the sun and then move to Mercury, Venus, and all that. And that will be a nice one. And that one's done by Free School, and it's very just small little increments of each one of the things in our solar system, and I think it'll go right along with a good with our notes here. And that one actually has some good pictures of the sun, so I like that. So we just put a little bit of the sun and we moved on to Mercury. Now, older kids, you've already done Mercury and you've already done Venus. So this is just going to be as a review. But if you were absent and didn't get any of this done, you can do a page on this, and then that way it will get glued in. Now this, as you see, I was starting with the star world. We started our solar system from the star out, which is our sun, and then we go to the planets, which originally they called the planets the wanderers, because they thought they were stars at first, but they were moving in odd patterns, and it wasn't exactly what they were seeing with what we would call the regular star category. So now they have a new name called wanderers, which is what we have the word that means planets, or the word planet means wanderers. Okay, so our first wanderer, Mercury. So we already went over this. Mercury is 2/5 of Earth's diameter. So small little guy, no atmosphere, and so it's either freezing cold when you're away from this, when you're faced away from the sun, or you're burning up if you're near the sun, or your face is towards the sun. So it's not going to be the most habitable place. It is noted that it's the speediest planet, and so that's kind of cool. So he's he's a little fast guy, and you can see each one of the planets. What I'm going to be doing here is I'm going to be always giving you the orbit. Now, if we remember when we talked about how this the laws of planetary motion that we saw with Johannes Kepler, we know that there's a motion about this whole world, our whole solar system, our whole universe, everything. Just as there's motion everywhere. And there's certain laws of motion that we can track. And so remember when we talked about, okay, that would be the sun, and that Johannes Kepler and some of the other great astronomers figured out, originally they thought everything was kind of going around the sun in, nice little circle patterns, and everything was flat. And they started realizing, wait a second here, the math isn't working out. It doesn't seem like everything is as circular as we thought. And that's when Kepler realized that it's really not a perfect circle. Many times it's an ellipse, kind of like an oval shape. Do you remember that? And we took this, and I'll lift it up to help with the colors here, but we tried to take the particular planets or even some of the dwarf planets and to create color by color their particular orbit. So the orbit is going to be the way I go around the sun. So that's one movement of the planets. But then you don't have just how do I go around the sun. You also have the fact that you're spinning in a circle, which is called a rotation. So each time I talk about a planet, I'm going to say, oh, how long does it take to get around the sun? What is its orbit? And we're going to use Earth days so that we can compare, so we understand, okay, well, if it would take this many Earth days just for him to get around the sun, then that will help us understand it a little bit. And once we get all the way out here into Uranus and Neptune, it's going to take a whole lot of time just to get around the sun because they're so far. And if you remember from Kepler's laws of planetary motion, the farther you are away from the sun, which makes sense, the longer it's going to take for you to get around. Now, that doesn't mean you don't spin fast. You can be a fast spinner for your rotation, but your orbit, if you're that far away, then it's going to take you a long time to get around. The closer you are, like Mercury, then you'll be able to get around faster. And of course, this has all to do with the theories of gravity and such in this planetary motion. So when we look at a planet, we're always going to have that reference so that we can kind of see who's going around the sun fast and who's also spinning fast or spinning slow. So if we look at Mercury, if you remember, and remember I had some of this math mixed up and I had to fix that, you older kids. I was trying to make sense of what am I saying here when I had 176 here and 176 and I had to switch those to 88. All right, so that goes along with 88 Earth day orbit. So the orbit, meaning that Mercury gets around the sun, it only takes him 88 days. But the weird thing about it is, it takes 59 Earth days for him to just spin. Okay, so if you're picturing, and I should have got a couple little pretend little planets for this, but I'll use a little marker cap here. So if I'm saying that this is Mercury, so it's going to only take 88 days for him to get around the sun. So he's pretty speedy. But while he's going, he's kind of slow. For as fast as he's going this way, he's kind of slow in his own spin. So in his own spin, he's just spinning pretty slow. And it's 59 Earth day rotation. So that means as he's going so fast like this, he's kind of not spinning too fast this way. So if you were on Mercury and say you were staying there and say you could and not freeze to death and burn your face off like we know would happen, then it would be 88 days of day because you're spinning too slow. And so you're still looking at the sun because you're not spinning fast enough. And then it would be 88 days of Earth night, right? And so one night would take 88 days. So you'd be in the darkness for 88 days, and then you'd have 88 days of sun. This is, again, of course, if you could last even getting near it, let alone getting on it. And so each time I'm going to give that reference so we can say, okay, Mercury, he's going super fast around the sun, but he's a slow guy when he's just sitting there spinning on his axis, right? The other thing we can see about Mercury, if you remember, he's more eccentric. Remember, we talked about it being more eccentric and more stretched out. And so your ellipse is going to not be very circular. So if you remember on this, we had those really stretched out ones, and then we had ones that weren't as stretched out. And so it just depends. And so each planet, some of them are really eccentric, and some are, which would be stretched out, and some are more circular, and they're not as stretched out. And the same thing goes along with like the shapes of things, like when it comes to planets or asteroids or moons, it depends on your density. So how big you are and how much mass you have is going to create, when you are spinning in your little rotation, the shape you end up taking on. I always think of like the rolling of stones. If you want to roll stones and make them all nice and smooth, you keep rolling them, rolling and rolling, rolling, and it smooths out the rocks. Kind of like that, the planets and the way that their masses and the constant rotation. We have different types of shapes that end up taking place. And some are more circular, some bulge a little bit, but then we also have the difference between the orbits. Some are more stretched out, some are more circular, so lots of different sides to the orbits and the rotations and the shapes. Right? Okay, so temperatures, because we know it's freezing and super hot, we have super hot, 800 degrees Fahrenheit, so you can wear some good sunblock that day. And then at night, you hope that you have some good protective gear, because minus 275 degrees Fahrenheit. So not a very good habitable situation. Then we got Venus, and Venus, we already did this one. I just added a few extra things here on mine that I saw was not on yours. We might have ran out of time. But Earth's twin is what we say it is. And not because it's a habitable and wonderful place, but simply because of like the size and a lot of the things that a lot of its characteristics. But it's a terrible place, terrible. Remember we talked about this? The atmosphere and having the sulfuric acid that would melt off your face, and the lightning storms and the really high atmospheric pressure. We'll talk about that. So it's Earth's twin, but yeah, one we'll call Earth, this Venus the evil twin, and we'll call Earth the beautiful, kind, whatever twin. Okay, so here's the same thing I'm going to do with all of them. 225-day Earth day orbit. So that means it only takes 225 days for it to get around the sun. So that's, I would say, like a medium amount, because ours is 356 days to get around. So we're close, a little faster than us. But the rotation, if you look at the rotation, 243 Earth days. Now remember when I told you that Mercury was kind of spinning slow on his little axis and his own little his own particular spin? This guy is really spinning slow. 243 Earth days to make one rotation. So as he's going around, if we picture him again with my cap, as he's going around, he's barely doing his own little spin. Like we know they have their own spin plus the orbit. So that guy's slow, right? So the other thing that's interesting is that it's retrograde. So whenever we see retrograde, it means it's kind of going backwards, different than what's normal. So instead of going west to east, he's going east to west in his particular movement. Okay, again, the atmosphere, sulfuric acid, there's my little clouds, so that's not, so your clouds are filled and raining down sulfuric acid, a lovely place. And then we have the lots and lots of storms, lots of lightning from all that friction and the cloud movement. It does say that he's a more circular orbit. So he's with Mercury, it's more eccentric, and then Venus, his orbit is a little more circular than any other planet. I like this atmospheric pressure. It's kind of hard to see there. We have 1,330 pounds per square inch. So this would be, and you remember our little can thing that we did, our can experiment, where we crushed the cans? And if we think of our atmospheric pressure, which is what, 14.7, I think? Would have to look that up to make sure that's correct. But what I do know is this atmospheric pressure is 91 times greater than ours. So remember when we removed all the water and the air got out of the can, we flipped the can over, the can went and crushed? Okay, that's with only a small amount of atmospheric pressure. So imagine if we did that experiment on Venus, if we didn't have our faces melted off and all. And our can didn't melt, and our little tongs and our little heater thing we needed to put together for our wonderful experiment. That thing would be some serious crushing there. 91 times greater than the Earth's atmospheric pressure, the pressure of the air sitting on you. So you can't go there anyway, not just your face melting off and all that, but you're crushed into a can. Yes, so you would be the can. See? So this isn't our first spot for a vacation if we ever get to tour the solar system. Let's just do a flyby on that one, okay? All right, so that's our first two. So we had the sun and then our first two inner planets. And then, now the problem is going to be with continuing on in this. And I'm only going to make this video on just our solar system, this part of it, and then I'll be making videos for each one of the topics so that it doesn't go too long because it's going to take a little while. Of course, you can always pause it and then come back to it whenever you need. But with this, we had already glued in, you know, obviously the little craft that we were doing, we'd already glued in this 2-page that we worked on in understanding the elliptical orbits, and we had the, you know, the solar system right out here, which I did not finish. I'll do that. But we had planned on using these little sides for notes too, like for what Earth's notes and then Mars notes. That might be a little hard because I don't know if you want to get too crazy on like, okay, this note, you got to make this 2 inches because this is going to get glued here and 2 inches. So if you want to just listen along on this one, I was thinking since normally if we wouldn't have already glued all this in and already had lots of pages already set, then I would have just made a new page and just left this one and put some, you know, other stuff around it. But we had already done this before the school closing started. So if you want to just listen along on this one, I can always photocopy my notes for Earth and Mars and just glue them in everybody's little side journals. That way we don't have to get specific on trying to create a certain size for this little side guy. And then from this point on, we'll just kind of keep it where it's just a half page and make it pretty convenient, okay? But just so we go through this quickly, now we don't have to spend a lot of time on Earth because we already spent almost the whole year. So we kind of know Earth really well. But what we want to do is talk about Earth from a space perspective. Okay, what's this little planet that we've been studying all these amazing processes and getting all excited about? Well, maybe you haven't been getting exciting, but you know, Miss Jody, of the atmosphere and the hydrosphere, and oh my word, you know, we're living in an ocean of air. We live on the bottom. We're benthic creatures of the ocean of air. How amazing is that, right? Benthic meaning the bottom dwellers. So very exciting stuff. So we've been learning all that, but in the perspective of space, we want to look at it a little differently. So same sort of a breakdown. We want to see, like, you know, how big is it? How's its orbit and all that? So it's 8,000 miles in diameter. There I go with my words. The 5th largest, the largest of the inner planets. So if you remember, and I realize that I did not finish my bottom thing. You guys all have great drawings here. But remember, we were just trying for memorization to get a pattern of keeping track of from the sun out. And I did not finish mine, but we have Mercury, Venus, Earth, Mars, and then it looks like I started the asteroid belt and never finished it. Imagine that. But so when we say it's the largest of the inner planets, what we're talking about is these first 4. Remember, we got to set a pattern. We got 4 planets. We got a belt, the asteroid belt. And then we have Jupiter, Saturn. Oh, well, that wasn't a good way of making Saturn, because I don't want to mess up my rings here. So, oh, I guess that's not too bad depending on where it's at. Okay, we'll keep it. So Saturn, and then Uranus, and then Neptune. Of course, it won't be all nice and to scale because this is just for memorization, and we couldn't do it to scale anyway. So we have Jupiter, Saturn, Uranus, and Neptune, if you remember we did that. And then we said there's another belt that's been discovered, and this belt we call the Kuiper belt. The Kuiper belt. And then we talked about the theoretical Oort cloud all the way out here, if you remember. The Oort cloud being this idea of more like a thing that surrounds the whole solar system, like kind of like a donut in a sense, going upward, downward, every which direction, and having more things in that Oort cloud, and maybe that being the explanation for comets and that we see long-term comets. So we'll look at that when we look at the comet when we look at comets and study that later. But if you remember that, we did the pattern so we can memorize it. So we got 4, Mercury, Venus, Earth, Mars, and then asteroid belt. Then 4, Jupiter, Saturn, Uranus, and Neptune, and then Kuiper belt. So 4 belt, 4 belt. and then the lovely little Oort cloud theory. Right. So when I'm talking about the inner planets, it's the largest of these inner guys. Not the largest of all the planets, because once you go past this belt, then you're talking real crazy. We got some big giants out there. And in fact, they're going to be called the gas giants because they are very giant and there's lots of gases involved. You'll see. All right. So the largest of the inner planets. Now, the Earth is approximately, and not at all times, because we talked about this before when we were learning about thermal energy coming into our system, that energy is coming in and it depends on where you are in your orbit. So as Earth is rotating, and I'll use one of these bigger ones out here, like who is this blue guy? Neptune. So as Neptune's orbiting, depending the closer he gets to, there's times when he's going to be a little closer to the sun, and times in his orbit he's going to be a little farther away. So the Earth has that situation going on. And so we average it. So on average, 93 million miles from the sun. And we actually use that as our astronomical unit because that's something that's fixed to us. So that means that distance equals 1 astronomical unit, which is a unit to help us understand these bigger distances. Because after a while, if we keep, if we want to start saying, okay, well, how far is Pluto? How far is Eris? And how far is the next star? We're going to be writing lots of numbers with tons and tons of zeros. It'll be like, 2.4, 0, 0, 0, 0, 0, 0, 0, 47 zeros later. That's going to be a little rough. So we start making a new unit to help us understand these distances because they're so vast. So, but at this point, we can still talk miles. It's only 93 million miles from the sun. And we thought we were pretty close, and we do look close to the diagram, right? So our orbit, which we already know this, is 365 days, which is really has an extra 5 hours and 48 minutes into it. Not everybody realizes it's not exactly 600 or 365 days. There's a little bit, a couple more hours going on there, almost 6 hours more. But that's all right. We still average it to about 365 for our orbit. So it takes us 365 days to get around the sun. And we are cruising. Our speed is 66,600 miles per hour. So that's a speeding ticket for sure. And it's weird because we don't even feel like we're moving. We don't feel like we're rotating. We don't feel like we're orbiting. And as we see in lessons before, and as you'll see more when we get into more physics, all motion is relative. Like from this point, I feel like I'm sitting here at my little contraption I made to make our video, and I don't feel like I'm moving at all. But if somebody was watching me from the International Space Station, I'd be moving, wouldn't I? The whole Science Center would be moving because the whole Earth is moving. So motion is really relative. So, but we're on a little speedy planet here, and we don't even know it. So I think, well, I'm pretty fast at this point as long as the perspective and my reference point is out in space. I'm looking down at Earth. I'm a pretty fast mover. Okay. Well, anyways, so this is our orbit, 365 days, moving pretty fast. And we have a 24-hour rotation. So that means it only takes us 24 hours to spin on our little axis. And of course, we know that as night and day, 24 hours. We are the only planet that we know of that's suitable for life. And we talk about our planet in what's called the Goldilocks zone. So the Goldilocks zone is an area between the sun and the planet where the distance is just right. Like if you want to live on Mercury, of course, let's pretend like it had an atmosphere, it was fine, and we could live there. You would, like the story of Goldilocks, you would be like, oh, Goldilocks, she sat in that first bed and it was too hard, and then she got in the other bed and it was too soft, and then she found one that was just right. Well, this is how you would say with the Goldilocks zone of the Earth. You would get on Mercury and be like, oh, too hot, and then you would get to maybe you go to Jupiter, too cold, or Mars. But if you got to Earth, you'd be like, oh, just right in the place where we get enough thermal energy coming from the sun and coming solar radiation but then not too much, right? Because we know when we learned about the atmosphere and the energy coming in and weather and all that, you don't want to get too much of that because then you're going to be in some trouble in many ways. And so Earth is in what's called the Goldilocks zone of our particular sun. And it's amazing how perfect we fit in that spot, and that we have that perfect suitable planet for life. It's amazing. We do have an atmosphere. We already learned all about the atmosphere, so we're not going to talk a lot about it. But if you remember in the composition of our air, 78% nitrogen, 21% oxygen, and less than 1% of other gases. And then we learned about the blankets of our atmosphere laying on us, the big 5 blankets, the lithosphere, the stratosphere, all that, and keeping us nice and protected and warm and all that good stuff. So we have this wonderful atmosphere. And then we learned about the water, the hydrosphere, if you remember. So our planet has all this great water on top of that wonderful atmosphere. And so we're pretty set in this beautiful Goldilocks zone. We do have a moon, and the moon is called the moon. Now, moon actually means natural satellite. That means a satellite means you're going around something. So the moon is going around the Earth. So it's our satellite. Now you can have artificial satellites going around the Earth too. And those are satellites that we put up into space for our TVs and all that and our telescopes. So there's artificial satellites, but our natural satellite is the moon. Now, since that's what the definition of the moon, and that was the first one that we knew about, we just kept calling it the moon, which is a noun describing it, not its actual name. But once we started finding other moons around other planets, then we had to name them. We can't just call them all the moon. Then you go to Jupiter and you're like, oh, 60 plus moons. You're like, that moon, this moon, that moon, that moon, this one, that moon, 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 moon. What's that one's name? Moon. What's that one's name? Moon. What's that one's name? Moon. So you have to start naming them. But our little moon got the first name. It got the noun, which means the natural satellite. So we call ours the moon, and everybody else needs a real name. Now, I think there might be one that isn't named. I think a couple, definitely with the dwarf planet, one of them, Pluto, one of Pluto's moons. I can't remember, but not everyone has a name, but most of the moons from other planets are named, so they keep track of it. Okay, so then moving on to Mars. So Mars is half the size of Earth, and it's a reddish orange planet, which we're real familiar with. And we look at Mars and we say, I'm going to try to move this up a little bit just because it's going to be kind of blurry because I had to make it small since it's on the side notes here. And that's due to the iron-rich soil. And if you remember Fe, we always try to write the elements in a little box so we get used to that for the periodic table. So Mars has lots of iron in its rich soil. And when iron goes through its process, we call oxidation, we have a little rusty stuff going on and creates that reddish orange. Now, Mars has a 687-day Earth day orbit. So that means it's a lot slower in its orbit getting around the sun because ours is only 356 days. So it's taking a longer time to get around the sun, but his rotation is similar to us, 24 hours and 37 minutes just to rotate in place to do a day and a night. So that's cool, similar to us. The temperatures. See, Mars, we all want to go to Mars and we want to, figure out Mars and maybe colonize Mars. And I guess it's our best choice. I mean, what are you going to do? You're not going to go that way to Venus because, wow, you don't want your face just running off and burnt right off and all that in the toxic atmosphere. And you can't go to Mercury because that's too close, too cold, too hot, no atmosphere. So I guess you go to Mars. I guess that's your choice. That's the next one past Earth. We can't really get too far because these are big distances. So we can't just be like, well, if we want to go and live on a new planet, we're going to pick Uranus. Well, not a good choice either, but I don't think you're going to have enough supplies in your your space technology to get you there and back without you running out, because it would take at least 6 months to get to Mars and 6 months to get back. So you'd have to have enough supplies to, like, for the ride, food, water, all the stuff you need, and then for the ride back. So Mars is kind of, you know, our only choice at this point, since we can only go so fast in our space technology. All right, so, but it's not really the best when you think of it, because you've got some varying temperatures. It can get down to minus 125 degrees Fahrenheit. That's cold. Okay, so it can get really, really cold, and then its warmth time, and you know, and the days is only 23 degrees Fahrenheit. So like your whole life, like, is winter there. You're never gonna get out and play in the sun, and you're never gonna lay out or whatever. But why would you want to? Because when you really look at the atmosphere, you can't even really go outside, because it's not the breathable, wonderful atmosphere that we have. And I'll talk about that in a second. Mars does have 2 moons, and these are familiar. I'm sure you've studied this before. I just like the fact that they're really irregularly shaped, and the book says they're like potatoes. I love that. But they are. Some things in space are not perfectly round, and that is one thing. In order to be called a planet, that's one of the characteristics of a planet. It has to be nearly round. It has to have enough mass that it pulls itself in its spin, that it creates a nice little rounding. It doesn't have to be perfectly round. It can bulge a little bit and all that, but we're not going to be naming any potato-looking things in space planets at this point. And that helps us because there's so much out there. We don't want to start naming everything a planet, because then we got to memorize about 1,000 things on our charts. That's going to be too much. Right now we only have 8 planets, and that's good enough. And then all the dwarf planets that are being recognized, I think we have 5 at this point that we have to memorize. And then, of course, we've got comets, and we've got asteroids, and we got all those things. That's enough. We don't want to just get crazy and start naming every little flying potato out there, right? So, and of course, it's a moon on top of it, so we wouldn't be naming it a planet. But if we do find something that's like the shape of a potato in the asteroid belt or whatever, we're not going to call it a planet. So it has a very thin atmosphere, and so it doesn't have a lot of atmospheric pressure. So remember, the atmosphere is like blankets laying on you. So if you have a very thin blanket on you, it's not pushing down on you as much as what Earth's atmosphere with 5 blankets laying on us. It's nice. It's a nice lay, the air laying on us, but it's not too bad. But this one's very thin. So it's 159 times less than the atmosphere. So instead of the can crushing, it wouldn't, if you had something a little bit softer, more pliable, it would probably expand in that environment. And so nothing pushing it down like it normally would be. Now with the atmosphere of Mars, we have 95% of it is carbon dioxide. And with carbon dioxide, this is not something that we can breathe in. And so it's not good for us to have high levels of carbon dioxide. So it's not a great go play outside. You're going to freeze anyway. But also you're going to not be able to breathe. And the atmospheric pressure and all that's too light, and you get all kinds of crazy things. Also, it's violent dust storms, and it's a very dusty, crazy place, and at times these dust storms can last for a long time. And so we would, if we decide to go to Mars, which we are doing that, not me personally, but hopefully you guys will be on the team, and then when you're there, you'll be like, Miss Jody told me it was going to be rough when we had to live inside, and we have these 2 flying potatoes around us. No. But so the violent dust storms would be a real problem, and we would have to prepare for that. Mars is what people would call completely barren. We do have probes that have already went to Mars and robotics that have been traveling and mapping Mars and showing us what we have there. So we have a lot of information on Mars. So I think it'll still be very interesting exploration and worth our time, but definitely not going to be the best. I mean, it's no Goldilocks zone there, if you know what I mean. All right, so, and then moving on. Now, if you look at my journal, I don't have the little planets that we made, but I'm going to show you Lily's journal here. Lily, good job on this little art project. I like that. And then that's your little diagram. But you remember we started making some little illustrations of our inner planets. So that was Mercury, Venus, that wildness, Earth, and then Mars there. We had already glued these in again because this is where we're going to put some pictures and we were going to continue some notes on here. And so those are already in your journal, not in mine yet. I don't know if they made an extra set for me, but I'll check that out. But you see I have them marked to where I'm going to be gluing them in. So on this page, I have notes that are all the way down the page, and if you're doing your half sheet for finishing out Jupiter, Saturn, Uranus, and Neptune, you realize that when we come back, we might have to trim it up a little bit because it's supposed to go here, and we already got Mars just sticking out there. So what I was suggesting for this page is maybe to the last two ones, Uranus and Neptune, kind of write them in a little box towards the bottom of your note sheet. That way, if we have to cut this one out, we can glue it over here where Earth and some of the other planets are, and we'll make it fit somehow, like maybe right there or whatever. So just try to do what you can. Of course, you don't have to write as much as I do, so your notes usually are a little bit smaller than mine anyway, except some of you really hardcore note takers. Which I totally get that because I'm a note taker myself. All right, so on this page, after the four inner planets, then we move on to the asteroid belt. And the asteroid belt, we're going to spend a lot of time talking about that specifically on a different page. So I just write asteroid belt. We don't need to write all the details there, but just so we keep track of it. Then after the asteroid belt, the first belt, we have Jupiter. Now Jupiter is the first of the gas giants past the first belt, and he's nice and big. And so he's the fifth planet from the sun, 11 times the diameter of the Earth. So going around his middle, 11 times that of the Earth. So he's pretty big compared to the Earth. It would take 4,331 Earth days to orbit the sun. That means 12 years. It takes him 12 years to get around the sun. So remember we talked about Kepler's law, talking about the farther, one of Kepler's planetary laws, the farther you are out, then the longer it's going to take for you to get around. And that just makes perfect sense, doesn't it? But you imagine they were figuring those laws out when they never were up there seeing anything and didn't have all the great technology we have to have had pictures and sent our probes to. They were figuring this all out with the math. I mean, talk about brilliant here, just trying to chart it all out. All right, so 12 years to get around the sun. And then, but here's the interesting thing. So he's so slow getting around that sun, 12 years, more than you've been alive just to get through, most of you, to get around the sun. But yet he rotates. He's a spinner. He's just spinning out of control. Every 9 hours and 56 minutes that's his rotation. It only takes 9 hours and 56 minutes for him to go bzz, and spin around. Bzz, bzz, bzz. So his days and nights are like really fast. Zoom, zoom, zoom. But then it's taken him a longer time to get around the Earth. Now, when I say he's slow getting around the Earth, that doesn't mean, I'm not saying he's moving slow. I'm just saying he's so far out there that it takes him so long to get around the sun. Now, in 1979, when Voyager 1 was doing this exploration, again, I have a video that will be attached to this lesson, and there'll be a lot of videos attached to this lesson, and this video I'm making is already going to be a long video for you to go through. So it might take you a couple days to get through these videos in this. That's okay. Take your time, and you just keep doing the lessons and, however many days you want to as we go along, and I'll just keep posting them until we get back, okay? But when I post this Voyager video, some of you've watched it before, especially if you were in space camp, this space exploration camp this last year with us. We were talking about this. The Voyager 1, where it's been, where it's going, how long it's been going, and then Voyager 2. So this will give us some updates on that video. So that'll be really interesting to watch, Voyager 1 and 2, and they've been going for so long. It's pretty amazing. But in 1979, Voyager 1 discovered that Jupiter actually had rings. And so this wasn't something we were able to see from the telescopes as much because they weren't visible. So that's kind of cool. So Jupiter, of course, all the gas giants have some sort of ring around them. So that's really cool. We usually always think about Saturn, but it's all of them. All right, so then it's the second brightest from the Earth. So if you're on the Earth and you look, Venus is very bright because it's it's closer, but then you got all this stuff going on with Venus and all the wild atmosphere and all that stuff. And then you have the second brightest one being Jupiter from Earth, from looking at Earth, but not necessarily out in space. All right, so the largest planet of our solar system, the atmosphere is made of two major gases and then other minor gases. And actually, all of these guys and the big giants, the gas giants, they're all made of these two particular gases plus a mixture of some other minor gases. Hydrogen and helium. Remember, hydrogen's the first one on the periodic table. Helium's the second one with one proton, and this guy has two. And so it's the start of the elemental world with helium and hydrogen. And we see that same thing going on in our sun, but a little bit different with the processes there of the fusion that we think is happening. All right, so there's lots of storm systems on Jupiter, and so it can be violent also. And of course, it's spinning so fast. That makes a difference there in the storms. And it has 60 plus moons. So lots of moons going around there. And again, they all have these names to help us keep track of them. So we don't just say moon, 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 right? And then there's Saturn. It's the sixth planet. It has 10 times the diameter of the Earth. And it's going to take 10,747 Earth days to orbit, which would take 29 and a half years. Okay, 29 and a half years to get around the sun. So even though I'm not saying he's going slow, he's just going to be far away from the sun. So it's going to take him longer to get around. But his rotation is only 10 hours and 39 minutes. So that's still pretty fast on the spin there. Saturn, of course, composed like Jupiter of hydrogen, helium, and but what's interesting is he's the least dense. That means he doesn't have as much of the atoms packed in to him compared to some of the other planets. And so they say if you could get a bathtub big enough to fit Saturn, it would float. Or if you could, find an ocean big enough to stick Saturn, it would float. So that's kind of cool because he's less dense. All right, in Saturn we have strong and fast winds, which temperatures, lots of strong winds, and the temperature is very, very cold, negative 285 degrees Fahrenheit, so super cold, not a place for life, obviously. You wouldn't anyway because of the composition and being a gas planet. Amazing rings, where Saturn is always famous for all of its amazing rings, and there's so many different rings, you just gotta how are you going to keep track of them? So what they do is they name them by letters, this A ring and B ring and all that, to keep track of them. They used to think when there was only the evidence of the rings being there, that they thought that they were like a big giant like full mass of rings, and didn't realize they were separated rings, individual rings. So it's kind of cool how they figured it out. They figured it out mathematically, surprisingly. Again, all of these great mathematicians, and if you're a math whiz, this shows how math, which is the language of science, can really give us more data than what we could ever imagine. So they figured it out, and then of course it was confirmed when we had the, I think it was Cassini was maybe the probe that went to Saturn and took the pictures. So we have some amazing rings. Saturn has 600 plus moons, and so lots of moons too, lots of moons in Jupiter, lots of moons in Saturn. And then our moons start to go down a little bit, and then in the last two, a tad bit. All right, then we got Uranus and, of course, Neptune. Uranus, the seventh planet. It would take 30,589 Earth days to orbit. That would mean 84 years to get around. So I thought that was 29 years is a long time. 84 years is about the lifespan of an individual. So, I mean, I'm hoping to live to 84, but that would be my whole life it took for Uranus to get around. And I'm not 84 yet, and don't you even think it. But if I lived to be 84, I'd be like, well, Uranus got around the sun in my lifetime, right? So that's a long journey. It will only take 17 hours and 14 minutes to rotate, however. So that's pretty fast. So he's got a fast, and if you think about Uranus, and I always draw a little side guy there, he is, not only is it retrograde in his rotation backwards, we have a tilt in his axis. So he's kind of like laying on his side. So his rings are spinning this way, up and down. Pretty interesting. So we got all kinds of crazy stuff going on. Now he's not perfectly on his side. It's like 95-degree tilt, but almost, right? And so that's kind of cool. And composed of hydrogen and helium. And what's interesting and why we get that blue color is they think that the layers of methane that we see on the planet, methane is the way that the light shines on it, and then some of the light's absorbed. The blue light is what's reflected back. And so it's got this blue, beautiful blue side to it. And only 27 plus moons. So losing a little of our moons there. That's better, because my word, how do you memorize all those moons? And then our last but not least, and I had to write small to fit this in, and this is because I already glued all that stuff in, thinking we were going to write around the edges of stuff, and not realizing we were going to have this quarantine time. But that's all right, we'll make it work. And what you can do too, if this is hard with taking notes, is just stop the video, write out what you need, and then keep playing it and listen to all my crazy, and then stop it, and then keep playing, and stop it, and keep playing. And so that way you don't get stressed out on trying to write all this. And of course you don't have, like I said, you don't have to write everything. Just write out some neat things about each one of the planets. All right, Neptune, the 8th planet. And this is the only planet that was discovered by math before we even knew it was there. Now we always use math to figure out everything, but to actually discover a planet because the mathematical calculations weren't really right. Like something was messing around with Uranus and tugging on it, and they realized, hey, something else has got to be out there beyond. And they were able to figure that out. And again, math showing its bright side. Speaking of, Neptune is a very brighter blue than Uranus. Okay, just had to put that little doozy in there. All right, so we have the same thing we always do. So 59,860 Earth day orbits. So that means it would take 164 years. So I won't even be alive to see a full orbit of Neptune, and unless we increase like our living capacity and all that, with you brilliant minds of the future that are going to take on things like that. But I don't know if I would want to live 164 years. I already feel crackety and old. But if I could live 164 years, that's how long it would take to get around the sun. But its rotation is 16 hours and 7 minutes. So it's still a very fast little spinner guy. So that's interesting. Composed of hydrogen, helium, and other gases like the other ones. Also a methane situation, the layers of methane. But this is actually brighter blue than the Uranus. And so there's something about the scattering of light that's creating the brighter blue, and scientists aren't exactly sure what's happening there. But we have 13 plus moons, so we really went down on Neptune's moons to only 13, and still has rings like all the other ones. I love this part, and it's kind of hard to see there, but they are saying about the volcanoes on Neptune, thinking they're spitting out liquid nitrogen. So I always think of like the science experiments with the dry ice, you know, the frozen carbon dioxide. And you've seen frozen, or not frozen, but liquid nitrogen, how it also sublimes like the dry ice and bubbles out. So I'm just picturing this liquid nitrogen just spitting out of these volcanoes, and just how awesome and cool it is on this blue planet. And, you know, I like all the bright colors and all the weird stuff like that. So definitely a place to visit. Not that we could ever, but if we could, wow, right? All right, so that ends our tour of the solar system that we needed to get through for that particular part of chapter 10. Now 10, we still have asteroids, comets, meteoroids, like I said, constellations and then galaxies and suns and all that. This book has a lot, and so we have to break it up, right? So that we're not overwhelmed and getting all of our stuff done, and so the videos aren't 17-hour long videos, and you're thinking, oh my word, Miss Jody, what are you thinking? So we'll break it down. We're going to end on that, and then when I do my next video, I'll start the next topic, which is asteroids, comets, and meteoroids. And then you can just keep going along, okay? And again, keep all your little note sheets for me, and if you do any extra work. Now, sometimes I'll be sending some diagrams, and if I send a diagram, like just flopping open to back in the weather time when we had the weather maps, if I send a diagram like this, let's say, in some of our studies, which we don't have a diagram today, and I am explaining it, then you could be doing this at home. And so that's why I'll be sending it as a PDF form, and you could just print it out. If you don't have a printer, you can try to just draw it out on a half sheet. Obviously not something this vast, but if it's an easier diagram, like when we were learning about how weather maps work, you could draw something like that out. But this will be good because if you can do the diagrams at home, then you can take your time with them. You know how we're always so rushed in getting all of our diagrams done and the colors on them. We wouldn't have to worry about that. It would be a lot easier to take your time, pause a video, color what you want if we're color coding something. So if I do send those, I will attach them in the Google Classroom as a PDF. So when you go to the Google Classroom, I'll be inviting you by email. You click on there's 3 parts of the Google Classroom. At the top, it says stream, assignments, and people. So there's 3 tabs. The work, if you follow the stream, it's like a whole bunch of stuff coming up like a Facebook feed or something. And you get confused on what's when and where. So if you click off the stream instead, click on the assignment tab. The assignment tab will show you all the videos. In this assignment, I'll have my video plus the other videos that you can watch on the Voyager 2 and the scaling of the solar system, and I have one on there about what it means to be a dwarf planet, because we don't have time to go over that in particular, but we do need to know that about Pluto and the other dwarf planets that are being recognized and stuff like that. So when I add those extra videos, those can be things, and if there would be a diagram, I would attach it there. Okay, all right, well, I miss you guys so much, and I'm going to try to also make some videos of our animals and how they're doing and stuff like that, so you can keep connected with us. And I hope that this doesn't last too long and we will be together again.